Hello, so today we're going to talk about absolute value graphs and how we can easily graph them from their equations. So here's the parent graph of the absolute value function, and this is described as y equals the absolute value of x. So for every value we plug into x, we have to take the absolute value of it, and our output would be the y value. So if we look here, we can kind of think of this when we're looking at parabolas. When we were looking at parabolas is our vertex. It's 0, 0. Notice our growth pattern here, over 1, up 1, over 1, up 1, over 1, up 1. And when we go backwards from that vertex point, we go back 1, up 1, back 1, up 1. So this one's actually, I think, a little bit easier in memorizing the growth pattern of the parent function. So let's take a look at the general form of this. The general form is going to be just like we described it in the quadratic section. We're going to have y equals a times the absolute value of x minus h plus k. So I know we broke this all apart with the quadratics, but today we're going to look at everything together. So hopefully remember that the k value moves things up and down. So the k value moves things up or down. Now if you look at the h value moves things to the right or left there. The h value moves things left or right. Now remember, the inside value always lies. That h value is always backwards. So when we think about this, we always want to tell ourselves that the inside lies. And the a value is our stretch or compression. Wow, looks like a 3-year-old wrote that. So let's just take a look at a few problems and see how we do here. All right, so let's take a look at our first example here. So we've got the absolute value of x, all minus 2. So thinking back to our general form here, hopefully you're thinking, well, this looks like the parent graph, but it is moved down 2 units. That's exactly right. So instead of that vertex point being at 0, 0, it's going to be now at 0, negative 2. And then we can build off that point by going over 1, up 1, over 1, up 1. We go back 1, up 1, back 1, up 1. So this one's actually fairly easy to graph. So if we take a look at how the graph actually looks, notice how our vertex point is now at 0, negative 2, over 1, up 1, over 1, up 1, over 1, up 1, back 1, up 1, back 1, up 1. So, all right, so let's take a look at the table that goes along with this and make sure this makes sense. So if you take a look at the table here, notice our vertex now is at 0, negative 2. Notice how when we go over 1, we go up 1. Over 1, up 1, that pattern holds true all the way through. When we go back 1, we also go up 1. We go back 1, we go up 1. So the pattern holds true. All right, so now let's take a look at the equation y equals the absolute value of x plus 3. So now hopefully you're thinking the inside lies. So if we're thinking about the parent graph where that vertex is at 0, 0, this one is being moved 3 units to the left because the inside lies. And then from that point, 0, negative 3, our new vertex, we go over 1, up 1, over 1, up 1. We also go back 1, up 1, back 1, up 1, and we have our pattern. So if we take a look at this, hopefully we see that we moved 1, 2, 3 units back. And then from there, we would go over 1, up 1, over 1, up 1, go back 1, up 1, back 1, up 1. So hopefully this seems fairly easy. All right, so let's take a look at the table and make sure the table makes sense from how we move this. So if you look here, notice our new vertex value is at negative 3, 0. So it makes sense that we went 3 units to the left here. So right here's our vertex. Now we go over 1, up 1, over 1, up 1. We go back 1, up 1, back 1, up 1. So the rule still holds true here. All right, so let's take a look at y equals 3 times the absolute value of x. Now this is a stretch factor. So our normal movement of up 1 over 1, like a slope of 1, is going to be changed into up 3 over 1. So let's take a look at the graph here. Now notice in blue is the y equals 3 times the absolute value of x. I kept the parent graph in red there so you can see over 1, up 1. And now I'll look at the y equals 3 times the absolute value of x. Our vertex point is still at 0, 0 because we didn't move it left or right at all or up and down. So over 1, up 3, over 1, up 3. So when that number is greater than 1, it stretches it. So it has a steeper slope basically. So let's take a look at the table here. Again, the blue numbers are the numbers of y equals 3 times the absolute value of x, and the red numbers are the parent graph. Notice our vertex is at 0, 0. And now when we go over 1, we go up 3, over 1, up 3. So this kind of defines our slope for the absolute value equation. So let's take a look at y equals 1/3 the absolute value of x. So when that number is in between 0 and 1, it has a smaller slope, so it opens wider. So if we take a look at the graph here, again, notice we didn't move it left or right at all. All we did was change the a value there. The red line is the parent graph, y equals the absolute value of x. The blue line is y equals 1/3 the absolute value of x. So notice here the slope is, you have to go up 1 over 3, just like the rise over run of a linear equation. We go back 3, up 1, so it opens wider. So let's take a look at a problem that mixes everything together, where we adjust the a, the h, and the k.
Okay, so let's take a look at this problem here that mixes everything together. Hopefully we see that it opens up and that we have a vertex point at -3, -2. So we'd have to go back 3 and then down 2 to get to our vertex point. And our parent graph, we would go over 1, up 1. Since this has a scale factor of 2, we have to go over 1 and then up 1 times 2, which would be 2. So we go over 1, up 2, keep going over 1, up 2, over 1, up 2, over 1, up 2. And using the idea of symmetry, we can now flip all those points over our axis of symmetry. And now we connect our dots. So now we can talk about the domain and range of this absolute value function. The domain here goes from -infinity to +infinity, just like a quadratic. The range, we have a low point at -2, so we include -2, and it goes up forever. So our domain is -infinity to +infinity, and our range is from -2 to infinity. Okay, so let's take a look at this problem. Notice we have a -1/2 as our a value, and we have a -2 on the inside of the absolute value and a +3 on the outside. That means we need to go right 2 and up 3 to get to our vertex point. This also means we're opening down, and we need it to have a slope of down 1, right 2, down 1, right 2. And then we can, using the idea of symmetry, we can flip those points over. Down 1, back 2, down 1, back 2. Remember that the inside lies. That's why we went right 2. Then we connect our dots and we are done. So now let's take a look at the domain. The domain, it goes back forever and forward forever. So we have from -infinity to infinity would be our domain. Now the range here, we have that high point. We have that maximum spot. So that is at +3. And notice how it goes down forever. So our range would be from -infinity to positive 3, and we would include positive 3.